Okay, let's go ahead and get started. So, just an announcement. I have solutions up here for problem set 4. So please, if you didn't get one already, come up after class and get one. I also have solutions for the first 3 problem sets if any of you have missed those. The first 3 problem sets have been graded. There's a few that haven't been picked up, so you can pick those up here. Or for those of you listening at home, I guess what I'll do is I will leave them in the box outside my office. The place where you usually turn your problem sets in, I'll leave these graded ones in the box outside my office so that anyone who has not picked them up in class can pick them up there. The TA is right now working hard grading problem set number 4. It will be done by Monday in time for you to pick it up. So the TA who's grading that one is Julian. His office is on the 4th floor. I forget exactly which number, but it's in the syllabus which I handed out and which is on the web page. So what you can do is stop by his office to pick up your graded 4th problem set by Monday. So he said that he'll be around his office most of the day Monday, and that if he's not in his office, he'll leave a note on his desk to let you know where he is, because he might be in the lab or something like that. But if you just stop by his office on Monday, you should be able to get the 4th problem set back if you want it. However, there are solutions which I handed out right now, so maybe you don't even need to get your problem set back. Okay, so that is just an administrative announcement. So what I would like to do today is, probably for the first half of this class, I will conclude our discussion of non-inertial coordinate systems and rotating coordinate systems. And then for the last half of this class, I will just very briefly give you a review of those subjects which will be covered by the midterm on Tuesday. And that will also be a chance for you to ask any questions you might have about the midterm. Okay, any questions before I continue? Let's do some physics. So last time we discussed rotating coordinate systems. So just to remind you, if we had an object whose position vector is given by r, then we could write that position vector either in static coordinates as the sum over I, ri, ei prime, where the set of 3 vectors ei prime, where I runs from 1 up to 3, are the 3 coordinate axes of flat Cartesian static coordinates. Or we could write it in rotating coordinates as the sum over I, ri, ei, where these ei's are now the set of 3 vectors that describe the coordinate axes of a rotating coordinate system. These 2 different coordinate systems are related by the rotation matrix, which I called U. So the coordinate axes of the rotating coordinate system were given by the sum over j, uij, ej prime, where this matrix U was the orthogonal matrix which describes the rotation of the rotating coordinate system. So it is orthogonal in the sense that U transpose is equal to U inverse. Now, this matrix is a function of time, so we could define the matrix A, which was U dot times U transpose, This was an antisymmetric 3 by 3 matrix. So it could be organized as follows. So because it's antisymmetric, its diagonal entries were 0, and its off-diagonal entries are determined by 3 quantities, omega 1, omega 2, and omega 3, which define what we call the angular velocity vector, which is the vector whose components in the rotating coordinate system are given by omega I, where I runs from 1 up to 3. And the utility of this definition of the angular velocity vector is that if we have a vector v whose components are given by vi in the rotating coordinate system, then if we wish to write down the time derivative of that vector, it's just given by the sum of 2 terms. So there's the first term, which comes from taking the derivative of the components of that vector in our rotating coordinate system. And then there's a second term, which involves the fact that our coordinate system itself is rotating. And this second term is just given by vi times omega cross ei, where omega is the angular velocity vector. So using this, we could, for example, compute the acceleration vector, which is the derivative of the velocity vector. And we saw that this was the sum of 4 terms. So if I have an object whose position is given by the vector r, whose components in the rotating coordinate system are denoted r superscript I, then the components of the acceleration vector in this rotating coordinate system have 4 terms. There's the term where we take the second derivative of the components, ri, a term which is linear in the derivatives of ri, another term which is linear in ri, omega cross ei, plus a final term which is ri omega dot, all crossed with ei. Here, let me... So, I realized I actually said 2 stupid things at the end of lecture last time. This is what happens when I'm forced to deliver lectures immediately following lunch. The first thing I said, which probably none of you picked up on, but I felt guilty about nonetheless, was that the cross product was associative. This, of course, is not true. So if that statement means nothing to you, then remain happy. But in fact, it is important to remember that this term here is omega cross ei, which of course is not the same as omega cross ei. Omega cross omega is equal to 0. So the right-hand side of that equation is 0, whereas the left-hand side is not. So I misspoke when I said that the other day. The other more serious gaffe that I made, I'm a regular Sarah Palin up here, was that I actually got the name of one of these terms wrong. So this first term up here leads to a force proportional to omega cross v. So, for example, if I were to write down the body acceleration vector, which would be the sum on I, r double dot I, ei, then these other terms would cause fictitious forces to appear. So the total acceleration vector would be A body plus 2 omega cross V body, where V body is the vector whose components in the rotating coordinate system are r dot. The third term would be omega cross r, and the fourth term would be omega dot cross r. So these three additional terms correspond to three so-called fictitious forces. So this term here is the centrifugal force. Force, of course, would be in quotes there. It's not a real force. It's just a consequence of writing your equations of motion in a accelerating reference frame. This guy here is called the Coriolis force. And this term here leads to what is known as the Euler force. Okay, so this was just a reminder of what we covered last lecture. Are there any questions on this? So what I would like to do today is just perhaps give you a slightly different derivation of this exact same fact, now using our newfangled Lagrangian technique. How would we go ahead and understand the addition of these terms in the equations of motion from the Lagrangian point of view? So let's imagine that we would like to derive these additional terms directly from the Lagrangian. So let's imagine that I have some particle, some object, which is moving in some potential v. Then the Lagrangian will be 1/2 m r dot squared, so the kinetic energy, minus v of r. Or if I wish to write this a little more explicitly, in my static Cartesian coordinate system, this would be 1/2 m times the sum over I, ri dot prime, ri dot prime. The prime denoting the fact that I'm writing these coordinates in the static Cartesian coordinate system, which is not rotating. Now, let's say that I wanted to, so if I wanted to write down the equations of motion in terms of these static Cartesian coordinates, this is an exercise with which we are all familiar. You just write down the Euler-Lagrange equations following from this action, treating the Ri primes as our dynamical variables. So let's suppose now that I wanted to write down the equations of motion involving the Ri's rather than the Ri primes. Let's say I wanted to write the equations of motion using as my dynamical variables the coordinates of this particle in a rotating reference frame rather than a static reference frame. Well, that's something that we know how to do using our Lagrangian recipe. So we just remember that Ri prime is the sum on J, U, Ij, Rj. So if I wanted to compute Ri prime dot, so that I could go ahead and plug this back into the Lagrangian, I would have the sum of two terms. There's one term, which is U dot Ij, Rj, coming from the fact that my coordinate system is rotating, and another term, which is U Ij times Rj dot. And so then what I could do if I wanted to derive the equations of motion in this rotating coordinate system is I could just plug this expression back into the action, and treat my Ri primes as my my Ri's as my dynamical variables rather than my Ri primes. And just go ahead and turn the crank, and what you would find at the end of the day is that you would get precisely the same equations of motion as the ones I wrote above, using this expression for the acceleration vector. So this is a rather straightforward, yes?
Will you find U last time? We went to UJI.
Oh, yeah. Perhaps it's a transpose. Okay. You're right. I wasn't very careful about how I wrote my indices. And the reason I wasn't very careful about how I wrote my indices is that the sentence I was about to say before you asked your question was the following sentence. So let's not be careful about our indices and just derive this schematically. So roughly speaking, R dot is equal to the matrix U dot times R plus U times R dot. And the Lagrangian, if I just work schematically and forget about my indices, is 1/2 m times U dot R plus U R dot times U dot R plus U R dot minus V. Now, I will leave it as an exercise for the diligent student to go ahead and put all of the indices back in and make sense of this expression precisely. But my point is that I just want to show you that if you treated this as an action with R as your dynamical variable, you could then go ahead and write down the Euler-Lagrange equations in the way that you have become accustomed to, and see that you would get all of the various different Coriolis, centrifugal, and Euler forces popping out. So let's understand how that would work. So I hope you don't mind that I'm just going to forget about my indices for the time being. I encourage you, if you're feeling bored this weekend, to try and go ahead and put all the indices back in and write down these expressions precisely. But because I'm just rederiving something we already know, I won't bother to do that. So this Lagrangian is something like 1/2 m there times 3 terms. There's a U dot R squared term, a U dot R dot term, and a U R dot squared term. And then the Euler-Lagrange equations say that the time derivative of the derivative of this expression with respect to R dot, so that's equal to U dot R coming from the second term plus I'm sorry, there was a U squared here. U times R dot will be equal to the derivative of this expression with respect to U. So that'll give us a U dot R plus U dot R dot minus V prime. So I'm not keeping track of any factors of 2 or anything like that either. Yes? Yeah, there's U dot U. When I say I'm not being careful about my indices, that also means I'm not being careful about the order of my matrices. Right? Because the indices also tell us about the order of my matrices. I'm being very schematic here. And when I say I'm being schematic, it means that I get to not answer questions like, what are the orders of the matrices? How are the indices being summed over? So on and so forth. I just wanted to give you a 5-minute schematic derivation so you could see how these various different forces would arise if I had attacked this problem in a straightforward way using my Lagrangian recipe. So we then go, now remember, any other questions? Yes. So now let's just remember that U is a function of time. So when we take the derivatives here, what sort of terms do we get? Well, we get a term involving second derivatives of u, a term involving u double dot times r, a term involving u dot times r dot, and a term involving u times r double dot. And then we could move all of the other terms so you can see that this term is of the same type as that term, and this term is of the same type as that term. So what we see is that we'll get a sum of 4 different kinds of terms which are equal to v prime. There's one term which is u dot times r. So another term which is u times u double dot times r. Another term which is u times u dot times r dot. And then the sort of standard term which is u times r double dot. So if you went through the details carefully, you would see that this term here is the usual r double dot term that appears in any equation of motion. It's what I call the body acceleration. This term here involves the angular velocity, u dot, that's what I called A, which was the angular velocity matrix, times r dot, which was the velocity. So that's an omega cross v term, which was the Coriolis term. This term here involved u double dot, or the derivative of the angular velocity vector. So that was the Euler term. And this final term here involves 2 powers of u dot, so 2 powers of the angular velocity vector times r, and that is the usual centrifugal term. So I just went through this to convince you that I haven't done anything special here. All I have done in deriving the equations of motion in a non-inertial coordinate system is write my Lagrangian in terms of these non-inertial coordinates, and then use the straightforward Lagrangian recipe that I worked out for you at the beginning of the semester. So I'll just leave it as an exercise for all of you guys to put in all the indices and to check that you get all of the numerical factors and the cross products and all of that stuff right. Any questions on this? You can't expect me to do everything for you. You're adults now. You should be able to do some of this stuff for yourselves. Okay. So perhaps before I conclude our discussion of rotating reference frames, I can just do a few examples of problems involving rotating frames of reference. So there's a very famous example of a rotating reference frame, which is the reference frame at the Earth's surface. So the classic example of a rotating frame is that of the Earth's surface. So the angular velocity of the Earth's surface, well, let's go ahead and compute the angular velocity of the Earth's surface. Well, that's going to be 2 pi if we use units of radians. And if we want to evaluate it in inverse seconds, then we need to count the number of seconds it takes for the Earth to undergo a rotation by 2 pi, which is 24, the number of hours in a day, times 3,600, the number of seconds in an hour. And so that's something like 7 times 10 to the minus 5 radians per second. So let's go ahead and go through a few examples of problems involving the Earth's rotation. So let's consider the example of a mass which is hanging by a string at latitude lambda. Okay, so here's my picture of the Earth. And let's say that we're at latitude lambda, which means that if the North Pole around which the Earth is rotating is pointing vertical in this picture, then lambda is the angle of latitude, so it's the angle made with the horizontal axis in this picture. And as my rotating coordinate axes, I will take the z-axis to be the vertical axis at the Earth's surface. I'll take the y-axis to point north towards the North Pole, the axis of rotation. And I'll take the x-axis to point straight down backwards into the blackboard. So you can see that by making it point backwards, these three axes obey the right-hand rule. So z will be the vertical direction, y will be the northerly direction, and x will be east. So these are what one would call the body coordinate axes. So we now wish to write the angular velocity vector in these body coordinates. So you can see from this diagram here that the angular velocity vector will point in some combination of the y and z directions. The amount, so if lambda is equal to 0, it will point in the y direction. If lambda is equal to pi over 2, it will point in the z direction. And in general, it's just a matter of staring at this picture I've written here to see that it points in the cosine lambda, sine lambda direction for arbitrary values of lambda. And the overall magnitude is just this constant omega, which was 7 times 10 to the minus 5th, 5 radians per second that I wrote down earlier. And if we have a mass hanging by a string, let's just let that mass be located at the point 0, 0, r in body coordinates, where r is the radius of the Earth. Okay, so let's just compute, let's imagine that the mass is not moving, so that the Coriolis force vanishes, because the Coriolis force was proportional to the velocity of the object under consideration. So we just need to compute the magnitude of the centrifugal force. So the gravitational force is, of course, just minus mg z hat, and the centrifugal force is minus m omega cross r. Let's just work that out. So that's minus m omega cross the cross product of omega and r. So if you look at omega vector and r vector in body coordinates, then you can see that this vector will point in the x hat direction, and it will be proportional to omega r cosine lambda times x hat. And so then crossing that again with the omega vector, you get minus m omega squared r times cosine squared lambda y hat cross x hat, which is minus z hat, plus sine lambda cosine lambda times z hat cross x hat, which is y hat. So if you look at that, you'll see that what this means is that the centrifugal force will lead to two independent contributions to the force acting on this mass located at a latitude lambda. So the first thing you'll see is that if we have this mass which is hanging by a string, then rather than pointing exactly towards the Earth's center, it will be deflected to the south, namely in the y-hat direction, by an amount which is of order, well, let's just compare the strengths of these two terms. So by an amount which is of order omega squared r over g, which, if you evaluate this, say at a latitude of 45 degrees, this is about a tenth of a percent, a few tenths of a percent. So I think at 45 degrees it was about 0.03%. The other effect comes from the part of the centrifugal force in the z direction, which is proportional to cosine squared lambda, which means that the mass of the object is reduced. And it's reduced also by an amount of about 0.3%. So, of course, the amount of mass reduction will be largest at lambda equals to 0, which is to say the equator, and it'll vanish at the North Pole, or the South Pole, where lambda is equal to plus or minus pi over 2. Whereas this first effect, the deflection to the south or to the north, will vanish both at the equator and at the North and South Pole, because at those points, cosine lambda times sine lambda is equal to 0. Okay, any questions on that? So, of course, the mass reduction is something that is very, very difficult to measure. The deflection is actually not so difficult to measure. I think that if you climbed up to the top of this building and were very, very precise about your measurements, you could probably measure it. I don't know, maybe that's not true. I think it's true. I think it's not so hard to measure. What's that? The wind is probably, you have to do it on a very windless day, maybe in some sort of vacuum tube. That sounds like fun. Any questions before I continue? So this was an example of the centrifugal force. Let's also do an example of the Coriolis force. So let's imagine that rather than just hanging a static mass on a string, let's imagine we drop a mass from some high building and watch it fall, and ask how the Coriolis force alters the trajectory of this falling mass. So, of course, the Coriolis force is going to be very small compared to the acceleration and the force on this object due to gravity. So, to lowest order, the velocity of this falling object will just be the velocity of the object in the absence of the Coriolis force. So it'll be minus gt times z hat. So let's say that this object is dropped from the point x equals y equals 0 at some latitude lambda at time t equals 0. Then the velocity will increase linearly in the minus z hat direction as the object accelerates towards the center of the Earth. Then the Coriolis force is minus 2 omega cross v, which to lowest order will be minus 2 omega cross v naught, plus higher order terms that we will neglect in this approximation. And omega had a term proportional to z hat, which of course vanishes when we cross it with z hat, and a term proportional to y hat, which was minus 2 omega cosine lambda y hat. And so y hat cross z hat is equal to x hat. So we have a minus gt x hat. So this is 2 omega g t cosine lambda x hat. And this will be equal to the mass times the first order perturbation in the acceleration of the object. So if we expand the velocity vector, so it's v naught plus v1 plus even higher order terms, this will be equal to v1 dot, so that v1 is equal to omega g t squared cosine lambda x hat. Or if we want to look at the displacement of the position of the object, then this leads to a displacement which is equal to 1/3 omega g t cubed cosine lambda x hat. So, of course, there will also be a large displacement in the minus z hat direction, coming from the fact that it's falling in the minus z hat direction. But there will then be a correction to that, which comes from the Coriolis force. And you can see that the size of this force is proportional to cosine lambda and points in the x hat direction, meaning that this object will be deflected to the east in the plus x hat direction. So just to summarize, if you have an object that is hanging from a string, then it will be deflected to the south by the centrifugal force. But if you have a falling object, its velocity causes it to be deflected to the east by the Coriolis force. And if you go ahead and do this in the southern hemisphere, where lambda is negative instead of positive, then you will see that the opposite applies, and that an object will be deflected to the north due to the centrifugal force, and to the west due to the Coriolis force. I encourage you to go through and repeat that exercise for yourself. Okay, and indeed, I think for a tall building, for a 10-story building or something like this, this works out to be about a few millimeters. So it's pretty small, pretty difficult to measure. But something that, if you were a very careful experimentalist, you could probably measure. Any questions? Any comments? Okay, so there's one more famous example, which I would be remiss not to mention, which is that of Foucault's pendulum. Just like the book. Anyone read the book? Yeah, it wasn't very good. I don't know. I thought The Name of the Rose was better. It was okay. It was a couple hundred pages too long. Would you like me to go through Foucault's pendulum? Yeah, I think it's worth doing. It's a fun example. Let's do it. I've come up with a few neat tricks which will allow me to do it very, very quickly. It's one of these rather messy problems. I think there's an entire section of your text devoted to it. I don't know if he uses the same tricks that I use to solve it. There's also a very long problem in one of the exercises in the book, which is devoted to studying this problem. I don't remember if I assigned that on your problem sets. Maybe I do. If you're lucky, I do. So the problem is that of a spherical pendulum which is moving under the influence not just of gravity, but also under the influence of the centrifugal and Coriolis forces. So let's imagine we have some spherical pendulum here. So I will denote the position of the mass at the end of the spherical pendulum by x, y, and z. And the action of the spherical pendulum, so if I wanted to, I could write it out using spherical coordinates, as you have done many times yourselves. But it's more advantageous to use, in this case, the method of Lagrange multipliers and treat the x, y, and z variables as being completely separate. So in this case, the Lagrangian is 1/2 m x dot squared plus y dot squared plus z dot squared minus the potential, which is mg z. Now, I should be a little careful here, which is that these are in fact all primed coordinates, because the kinetic energy is x dot squared plus y dot squared plus z dot squared only in the unrotating coordinate system. And what we would like to do now is write down the equations of motion in the rotating coordinate system. And I will be able to write these down simply only by making a series of drastic approximations. So if I wish to write down the velocity in the body coordinates, that differs by the addition of a term proportional to omega cross r. That's just another way of writing down the formula for r dot in terms of r dot prime that I showed you about 10 minutes ago. So that means that x dot squared plus y dot squared plus z dot squared well, let's write it as following. Let's write the space velocity squared is x dot squared plus y dot squared plus z dot squared, the term where we square v body, plus terms that are proportional to omega. So there is the so omega, let me remind you, was equal to a constant times 0 cosine lambda sine lambda. So it had a component in the y direction as well as a component in the z direction. So let's first look at what happens when we cross this with the component in the y direction. You get cosine lambda 2 omega, because we're squaring, of z x dot minus z dot x. So omega cross r gives you, so in this case, so omega, so the cosine lambda term is proportional to y hat, so it's y hat cross the position dotted into the velocity vector. So that has two terms. There's an x times z dot term and a z times x dot term. Because of the cross product, they have opposite signs. And a similar term, which is sine lambda 2 omega times x dot y minus y dot x. Plus terms of order omega squared, which can be neglected. Now, the first approximation that I would like to make is that this term here can be neglected because z will be approximately constant. Because I will only consider the motion of the pendulum as it moves very close to the minimum of the potential. And if I do that, that means that I can approximate z squared by L squared minus x squared minus y squared. And then I can plug that in and get an expression for the Lagrangian, which was 1/2 m x dot squared plus y dot squared plus 2 m omega sine lambda x dot y minus y dot x. And then the potential term is just minus, well, we need to Taylor expand, well, we could write this as mg over L squared, x squared plus y squared. Is that clear? Everyone with me so far? So I've made two approximations. Yes?
Why did you neglect the term?
This term I neglected because z is going to be approximately constant. We could keep it in if you like, but z is approximately constant. And this is no, yeah. Well, z is approximately constant, and if z is constant, then the x dot term is a total time derivative, so it doesn't contribute to the equations of motion. Whereas the z dot x, I'll just take that to be small because z is going to be approximately constant. Yeah, thank you. I should have made that a little more clear. Okay, so within this approximation, it's now very easy for me to write down the equations of motion and to show you the exact solutions to the equations of motion. I should actually point out that a term of this sort, x dot y minus y dot x, this appears all over the place. This is the term in the Lagrangian that arises if you have a charged particle moving in a magnetic field. This is one of those classic examples of mechanics problems. So usually you're used to studying mechanics problems where the kinetic energy is quadratic in the velocity. This is the first example of a mechanics problem you've seen where the kinetic energy has a term that is linear in the velocity. This occurs when we have centrifugal forces, Coriolis forces. It also occurs when we have particles moving in magnetic fields. It occurs all over the place. So this sort of term is a favorite one of mechanics professors worldwide. So keep it in mind. You'll see it again. So let's just write down the equations of motion. So the x equation of motion will be the usual x double dot plus g over L x, coming from the first and the last term in this equation. And that will be equal to 2m omega sine lambda y dot, coming from the time derivative of the derivative, well, coming from that middle term. And likewise, y double dot plus g over L y will be equal to minus 2m omega sine lambda x dot. So let's look at those equations for a minute. So the right-hand sides of those equations look just like a pair of harmonic oscillators. Indeed, if you were at the North Pole, if you were at the equator, where sine of lambda was equal to 0, we would just have a pair of harmonic oscillators. But now the right-hand side says that there is some sort of source for the x harmonic oscillator that's proportional to y dot. And likewise, there's a source for the y harmonic oscillator that's proportional to x dot. So this would be an example of what we call coupled harmonic oscillators, where we would have two standard harmonic oscillators, but there's a very small perturbation proportional to sine lambda, which couples the motion of the two harmonic oscillators. And in this case, in fact, it turns out that there is a trick that we can use to write down the solutions of this system exactly. And this is a lovely little trick, which I encourage you to remember. So let's let zeta, I don't know if that's a zeta. I don't really know what a zeta looks. I don't know what the name for this letter is, so let's call it zeta. Let's let zeta be x plus iy. Then these two equations can be written as zeta double dot plus I times 2 omega m. Oh, I'm sorry, there's no m there. I factored out an m. 2 omega sine lambda zeta dot plus g over L zeta is equal to 0. So let's look at the real part of that equation. The real part of that equation says x double dot, coming from this term, plus g over L x, coming from this term, is equal to 2 omega sine lambda y dot, coming from this term. And the reason is that we have an I here, so that this is still a linear differential equation, but by including that I get that middle term to turn the x into a y. And likewise, that if you look at the imaginary part of this equation, you'll get the y differential equation. Is that clear? Okay, now this equation for zeta is an equation for a complex dynamical variable zeta, but it's an equation that you've seen many times before in this class already. It's the equation for a damped harmonic oscillator. The only difference is that the quality factor is imaginary because of this factor of I. So this is an imaginary damped harmonic oscillator. So you know exactly how to write down the solutions. They're the solutions of the damped harmonic oscillator. You just replace Q by IQ everywhere. In particular, the solutions are zeta is equal to e to the I alpha t, where alpha is a root of the polynomial minus alpha squared plus 2 omega sine lambda I alpha plus g over L is equal to 0. Now, let's work in the approximation where this term is very small compared to this term. Then the roots of this polynomial are given by g over L plus or minus 2 omega sine lambda. So, in fact, that g over L, sorry, I guess I should write plus or minus there instead of there. In fact, that g over L is really the square root of g squared over L squared minus 4 times 2 omega sine lambda. But let's work in the approximation where g over L is much bigger than that other term. So that means that the solutions look like a constant times the product of two terms. So there's an e to the I square root of g over L. I'm sorry, there's a square root there. Thank you. G over LT plus, minus I omega sine lambda t. So let's look at this expression for a minute. So let's consider the case where lambda is equal to 0. Then this would just be the usual expression for a harmonic oscillator. So the x part would oscillate with frequency square root of g over lambda. The y part would oscillate with frequency square root of g over lambda. And this constant here would just be a complex constant which describes the initial direction of oscillation. If that constant is real, then the oscillator will oscillate in the x direction, imaginary in the y direction, and so on. Now, let's ask how this term affects the answer. So, we're working in the approximation where omega sine lambda is very small compared to the square root of g lambda. So you could just think of this as a small change in the complex constant as a function of time. So let's say that at time t equals 0, the spherical pendulum will oscillate in the x direction. As time progresses, the angle of the pendulum in the xy plane will change. And it will change with period 2 pi over omega sine lambda. So just to summarize, the spherical pendulum will oscillate in the usual manner in the xy plane, but the axis of rotation, the axis of oscillation, will rotate with a period 2 pi over omega sine lambda. So the time it will take to undergo an oscillation will be, so that's in seconds, or you could write it as 24 over sine lambda hours. So indeed, there are several famous examples of this. If you go, I believe Foucault did his original experiment in one of the great, I don't know, it was in the Pantheon in Paris, where he demonstrated that indeed the spherical pendulum had an axis of rotation which was periodic with period, I don't know, whatever 2 pi over the sine over square root of 2 is, or 2 pi times the square root of 2 hours. And I think there are various science museums where this is set up. I know that I've seen one in the Science Museum in Washington, D.C. I think there are other examples which are set up where one can observe this effect. So I should emphasize that, I did a lot of dirty tricks to get this answer. Foucault's pendulum is one of these famous, slightly nasty problems. I chose this particular set of dirty tricks to present to you because it allowed me to use all sorts of nice little things like introducing x dot y dot minus y dot x dot terms in the Lagrangian. It allowed me to use complex variables to solve the system. It allowed me to use our knowledge about damped harmonic oscillators. So this is a set of approximations that I find very nice to use. But I encourage you to look in the book where I'm not sure if they use a different set of approximations. But there's certainly an example worked out in one of the problems in Chapter 7 of your book where they use a different set of approximations to get the same result. So this concludes everything that I had intended to say about rotating and non-inertial reference frames. Perhaps I should pause and see if there are any questions before I continue. No questions? A lot of people don't believe all of the various approximations that I make in this example. I've been pretty fast and loose with my complex variables and my approximations. This is a great exercise to go through by yourselves. I think it's very instructive. No other questions? Did you do this in your elementary mechanics class? It's one of these examples that's just a little too difficult to do in an elementary mechanics class. Okay, so at this point, we've got about half an hour left. So at this point, I really leave it up to you what we do for the rest of class. So just to remind you, there is a midterm on Tuesday. I handed out a set of practice problems. On this list of practice problems was a set of parameters which will govern the administration of this midterm. It'll be 80 minutes. No outside references are allowed. You may use a translation dictionary if you like. I do not think it will be necessary. The midterm is intended to be challenging but not impossible. It's only 20% of your grade, so it's not a big deal. Don't stress out about it. Have a good time this weekend. Don't have too good a time. So the material that's covered on the midterm will be that of the text up to and including section 5.2, or alternatively that set of lectures up to and including the discussion of Kepler's laws of motion for planetary orbits. So if you like, what I could do is I could just give you a sort of 20-minute lightning review of everything that we've done over the last month. Would you enjoy that? Would that be torment? Would you rather go? I'll give you an option. Okay. Anyone, if you would like to leave, you're welcome to leave. I mean, I don't have anything particularly planned to say right now. I don't have prepared remarks. I don't have anything written on my hand for me to read off of. Did anyone see that in the news? Sarah Palin again? Okay. Never mind. Okay. Maybe what I could do is just give you a sort of lightning review of the various topics that we have covered over the last month. We've done a lot of really exciting, beautiful material. I mean, you've really, I'm proud of all of you. You have really learned a lot of interesting physics over the last month or two. So we started with a discussion of dynamical variables. So dynamical variables are the set of continuous parameters that are used to label the state of a system. And the number of dynamical variables that is required to uniquely specify the state of the system is the number of degrees of freedom of the system. So here I will just list the various concepts that I think are important for you to know. Of course, this is a necessary but not sufficient list of concepts. We reviewed concepts of dynamical variables, of numbers of degrees of freedom. We studied systems which have constraints. So there are a variety of types of constraints. There were holonomic constraints, which were constraints where one could write the positions of the various parts of the system in terms of the dynamical variables. And then there were non-holonomic constraints, where typically the number of degrees of freedom was allowed to depend on time. And the nice thing about the Lagrangian method is that if you have a system with holonomic constraints along with a conservative potential, namely one where there is a potential such that the force in the r alpha direction is given by minus the derivative of the potential, then in such a case, one can construct a Lagrangian, which is the difference of the kinetic and potential energies. And from this Lagrangian, there's a very neat way of writing down the equations of motion using the Euler-Lagrange procedure. And so if you have n degrees of freedom, there are n Euler-Lagrange equations that one can write down, which take the form 0 is equal to d by dt, dl by dqi dot minus dl by dqi is equal to 0. So this was an efficient way of computing the equations of motion of a system. And given this Euler-Lagrange technique, it was very easy to see that energy and momentum are conserved in certain circumstances. So we defined the Hamiltonian, which was the sum over I qi dot dl by qi dot minus L. And this Hamiltonian has the property that the total time derivative of the Hamiltonian is minus the explicit time dependence of the Lagrangian. So if the Lagrangian has no time dependence explicitly, but only implicitly through its dependence on the dynamical variables, then the Hamiltonian is conserved. And this was our first example of Noether's theorem, where a conservation law was the consequence of a symmetry of the system. And Noether's theorem was one of the deep guiding principles for our study of mechanics over the last month. We also, as a second example, defined the momentum conjugate to a variable q to be the derivative of the Lagrangian with respect to qi dot. So that if the Lagrangian is independent of q, that implies that the momentum, pi, is conserved. And so this generalized notion of momentum conjugate to a dynamical variable q was a very general concept which encompasses both linear momentum, conjugate to which is conserved if you have a linear translation symmetry, as well as angular momentum, which is conserved if you have a rotational symmetry. Finally, we saw that the Euler-Lagrange equations have a very elegant formal interpretation, which is that if one defines the action associated to a path through configuration space as the integral between an initial and final time of the Lagrangian on that path, then the first variation of the Lagrangian with respect to these QIs was the Euler-Lagrange equation. So that, for example, a mechanical system will go through the path in configuration space which minimizes the action as a function over all possible paths. And this was known as the least action principle, or Hamilton's principle. And in order to derive Hamilton's principle, we needed to understand in detail various facts about functional derivatives and the calculus of variations. Finally, we also saw that there was an alternative formulation of the equations of motion of systems with constraints involving Lagrange multipliers. So I don't intend on going through all of that in detail right now. Is this useful to you? Are you finding this is like the greatest hits reel? What is it? It's the highlight reel. So this discussion of Lagrangians and actions constituted roughly the first 2.5 weeks of this course. We then proceeded to apply this discussion in various circumstances. So we started by considering various one-dimensional systems. So we defined the notion of an equilibrium point, which is a point where if you start with q equal to 0 and q dot equal to 0, then q will remain constant for all time. And such equilibria are divided into two classes, stable and unstable, depending on whether small perturbations around these equilibria will either grow in time exponentially or whether they will remain of finite size for all time. For a stable equilibrium, the small perturbations around the stable equilibrium were described by a simple harmonic oscillator whose equation of motion was q double dot plus omega squared q was equal to 0. We also considered the various perversions of the simple harmonic oscillator, namely the damped simple harmonic oscillator and the driven simple harmonic oscillator, and finally the driven damped simple harmonic oscillator. So for the driven simple harmonic oscillator, the most efficient way of writing down the solution to the equations of motion was to use the trick where we let Q be complex, and then we saw that these solutions were given by complex exponentials. So a e to the I omega t times some real exponential factor, which described the damping of an oscillation with time. For a driven simple harmonic oscillator, there are two techniques that one can use to find the solutions to the differential equation. So here we have an inhomogeneous differential equation. And so you need to take as your solution the sum of the homogeneous and solution with a particular solution of the inhomogeneous equation. And in writing down the inhomogeneous equation, there are two different things that you could do. You could either guess the solution, or you could use the method of Green's functions. So the Green's function was a very useful method for writing down solutions for the driven harmonic oscillator. And likewise for the driven damped harmonic oscillator. Finally, having dispensed with the harmonic oscillator and all of its variations, we considered the generic one-dimensional system, and we saw that there is a analytic expression for the solution of a generic one-dimensional system. In particular, because 1/2 m q dot squared plus v of q was equal to a constant, which is the energy, this could be solved for the time it takes the system to evolve from one point to another, q1 to q2, as the integral dq over the square root of 2 e minus v. And there's a factor of m in there that, let's see. Yeah, I guess there's a 1 over m, isn't there? Is that right, or is there an m? No, there's an overall m. Good. And this expression was useful, for example, computing the period of the anharmonic oscillator, as well as the pendulum, and various other interesting sorts of problems. And we also understood the utility of using phase diagrams to analyze the behavior of an arbitrary one-dimensional system. So the phase space of I guess a phase diagram is the language that you use in statistical mechanics. I guess we just call it phase space here. The phase space is the space of the QP plane. If energy is conserved, then it's useful to draw the contours of constant energy and think about the motion as the one-dimensional motion along a contour of constant energy. Finally, we moved on to discuss Noether's theorem in general. And we saw that if we have a continuous symmetry, which depends on a parameter S, then one can construct the corresponding conserved quantity, which is given by summing over the momenta, summing over the dynamical variables indexed by I of pi times the variation of the dynamical variable with respect to S. And this allowed us to understand all sorts of interesting different conserved quantities. On your problem set, for example, you saw how, so this expression for the conserved current, for the conserved charge is true if the Lagrangian is invariant. On your problem set, you understood how to generalize this to take into account the case where the Lagrangian is not invariant, but only the action is invariant. And you saw, for example, that the Hamiltonian was the conserved quantity associated with time translation invariance. But in general, this prescription allows you to write down the conserved quantity associated with any symmetry, which can be thought of as a continuous transformation of the dynamical variables of the system. A great place to apply this set of insights is to the two-body problem. So here we had two objects which were interacting via a central force potential. So we first reduced the 6 degrees of freedom, which were the two positions of the objects in the x, y, and z space. And we used the conservation of total linear momentum to reduce this to a problem involving 3 degrees of freedom. And then we use the conservation of angular momentum to reduce this to a problem involving 1 degree of freedom. And we saw that the equation of motion was equivalent to that of a particle in 1D with an effective potential. So we then proceeded to spend much of our time considering the special case of the Kepler problem, where the potential went like 1 over r. So in this case, we found analytic solutions, which were conic sections, so that, for example, the orbits of the planets are ellipses. And we understood various properties of these solutions, such as, for example, Kepler's laws of motion. So I believe that was an incredibly efficient review of about 5 weeks worth of material. So, you know, hopefully this is not the only review that you will go through before the exam on Tuesday, but you know, this at least will get your juices flowing and get you thinking about the various things that we have studied. You know, I really feel like the best guide in studying is the problems that I have assigned on the problem sets, as well as the lectures that I have given. And finally, there are all sorts of examples in the book which are already worked out for you. I recommend you go through those. There are various little parts of the book that I did not cover explicitly in class, you know, so I encourage you to go through those yourselves. Yes? You know, I did not use the phrase virtual work in my lectures. I did use the fact that the work is the integral of force along a path through configuration space. That is an important concept. I sympathize with you that the explanation of it in the book is not particularly clear, which is why I didn't use it in my lectures. I think it's good for you to understand. I think that you will be a better person for understanding it. Yes?
The TA all starts tomorrow or Monday?
The TA, oh yeah. Did we want to schedule them on Monday?
Yeah.
Would you prefer that? I'll ask I'm sorry, I forgot. Was I supposed to do that? Yes. Okay, I forgot to do that. I'll go see if I can find the TA right now and see if he can have them on Monday instead of tomorrow. You know, the other TA, Julian, will be in his office on Monday. If you want to pick up your problem sets from him, problem set 4, which he should have graded by then. So you could also, if you have specific questions, ask him when you stop by on Monday. Although it's not his official office hours, so I can't guarantee he'll have lots of time to spend. I'll ask the TA if he can do it on Monday. So Loisan is the one who is supposed to hold office hours tomorrow. I'll ask if he can do it on Monday. And I'll try and let you know as soon as possible. Your job is to send me an email. If I don't send you an email by the end of the day, send me an email to remind me. And if you don't hear from me, by tomorrow it's his fault. Okay. Any other questions? Sorry, I did say I was going to do that, yes. Any other questions? Yes.
How many questions is it going to be? Was in the past time typically an issue?
In the past, time was not particularly an... So, my goal is not to have this be an exercise in how quickly one can write. I really want to... you guys should just relax. Like, don't, go to a yoga class, chant your mantra, just don't stress out about it too much. It's not a big deal. You'll do what you do. It's fine. In the past, time has not been... Let's put it this way. In the past, people have not turned in the exam early. But at the same time, people have not felt that time was a particular issue. On this exam, I feel like time will not... I suspect most people will not turn the exam in early. But my goal is not to just see how quickly you can write, So I think that the exam will be challenging, but not particularly difficult. My goal is for most people to get most of it right. So just relax. It's only 20% of your grade. Come on. Nobody cares about this stuff anyway. Okay, any other questions? Okay, I'll see you guys on Tuesday. And you're going to email me if I don't email you back, okay?
And I'm going to email you.